Okay, this morning class we're going to look at derivatives and differentiability. So, just a real quick review of derivatives. We've talked about a couple things. We've talked about, first of all, what's referred to as the average rate of change, which is the slope of the secant line. We define the average rate of change or the slope of the secant as f of x plus h minus f of x over h. We could also use delta x, so it could be f of x plus delta x minus f of x over delta x. And then we got into really how we're going to use the average rate of change in calculus, and that's when they give you an interval from a to b. You can just do it the way you did in ninth grade, which is just really a y2 minus y1 over x2 minus x1. The only thing that's a little unique about this is that, in algebra, if I gave you an equation, first of all, we were just doing the slopes of lines, but in calculus, we're going to give you an equation, and then I'm going to ask you to find the slope between 2 points on this equation, which is referring to a secant line. And they're not going to give you the points, they're going to give you an interval. So they're going to say from -1 to 2. And you're going to be expected to actually calculate the values of those points. So for example, if I have this parabola shifted down to, I was to graph this parabola, and just imagine what the points would be at -1. So it looks like it's going to be roughly -1, -1. And then at 2, it's probably going to be somewhere, I think, 2, 2 if I'm guessing. But, that's really what you're after. Here's the slope of what the secant line is going to be through these 2 points at the endpoints of the intervals. So what you would actually want to do is calculate the actual points. So for f of -1, you'd plug it in. -1 squared is 1. 1 minus 2 is -1, which is what I was kind of alluding to on the graph. And it looks like that's what it would be if my graph, according to my graph. F of 2, and we're verifying it with the equation, obviously. That's why I'm actually plugging it in. So I'm not guessing, but I'm actually calculating these points. It looks like it was 2, but let's plug it in to make sure. 2 squared is 4. 4 minus 2 is 2. Sure enough. So these are those 2 points here that you can see. Here's one, here's the other. And so I want the slope of this line that passes through the 2 points. So you do your f of b minus f of a equation, which is just really y2, f of 2, minus y1, which is f of -1, over b minus a, which is really x2 minus x1. So here's your y2 minus y1 over x2 minus x1. And then you just plug it in. F of 2 is 2 minus a -1 over 2 minus -1. You already have that. We can simplify that. That's 3. So we end up with 3 over 3, which gives you a slope of 1. So that becomes our average rate of change or slope of the secant line. Then we moved on and we talked about what would happen if we took the limit as h approaches 0 of our slope of our secant. That gave us our limit definition for a derivative. So when we looked at this point, we said, okay, if we take the limit as h approaches 0 of f of x plus h minus f of x over h, then what we ended up with is these secant lines approach the tangent line. So we ended up with the slope of the tangent, which we defined as a derivative, dy dx, or f prime of x, which is really instantaneous rate of change. Moving down now, I want to talk about differentiability, an alternate form of a derivative. There are some functions where we have to check to see if the derivative even works. And if you remember, a derivative is a limit, so a derivative is not going to work when the limit doesn't work. So remember what we were really doing when we found a derivative. We were trying to find the slope of the tangent line. So if I imagine a tangent line here for just a second, and really what we were looking at these secant lines as they got closer and closer. So as I moved this point down, if I picked another secant line, and I picked another secant line, as these secant lines got closer and closer to the point, the limit was approaching the tangent line. So these slopes of the secant line were actually approaching the slope of the tangent line. Now here's where a derivative could fail. According to the alternate form of a derivative, a function will not have a derivative at a point. So let's say this point right here is my a comma p of a. I just used p for point. I don't know why I did that, but I just did. So let's say at a specific point we're wanting to find the slope of the tangent line. We're saying that that function will not have a derivative at that point where the slopes of the secant lines fail to approach a limit as x approaches c. So as this point is approaching this value, okay, and this should say as the limit as x approaches a, actually. Let's be consistent here. Let's change that to an a. So as this point is actually approaching a, if the limit doesn't exist, then the derivative won't exist. Well, when will a limit not exist? When the left and right don't agree. So if you were to check the secant lines from the other side, if it doesn't look like those secant lines are going to approach that tangent line, then the limit won't exist. Now in this example it will. If you check from the left and right, the secant lines are going to approach the same tangent line from both sides. So what we want to do is consider differentiability and in the 4 ways where it wouldn't work, which we're going to define this as non-differentiability. And it's kind of a long word to spell. We're going to find this as non-differentiability. So please write that down here, because we're going to look at the different ways differentiability is going to show up and how it's going to show up in the 4 following ways and where it's specifically going to be non-differentiable. And to do this, in a few minutes on some examples, we're going to have to use this alternate form of a derivative that I introduced last week, which is different from the limit definition up here, because it specifically allows you to approach a specific value instead of letting h approach 0. And it'll allow us to check a point to see if the derivative works. And it's the limit as x approaches a of f of x minus f of a over x minus a, provided the limit exists, which means we're going to have to check the left and right. So let's look at a few examples of where it's actually going to be an issue, and then we'll do some examples. So the first one's what we refer to as a corner, and you do need to memorize these. A corner is the first place where differentiability is going to be an issue. And let me just come down here in some blank space and show you a corner, what it looks like. Example of a corner is f of x equals the absolute value of x. A corner is really just a sharp turn. It's when the graph has a sharp turn. And really, the reason this is going to be an issue is if you get a sharp turn, the slopes change drastically. And when they change drastically like this, the limit from one side is going to be an issue when looking at the other side. For example, if I was to check, let me change the color of my pen for a second. So if I'm to check the right side, if I look at the derivative from the right at specifically 0, where the sharp turn occurs, so there's my corner. If I look at the derivative from the right, the slopes of the secant line are always going to be 1, and the reason that's going to be the case is because it's a line. So since the slope of the secant line is a line, the derivative is also going to be a line. So as you look at the derivative from the right, the derivative is 1 as you approach 0. The slope of the secant line is 1, the derivative is 1, and as you approach 0 it's 1. It's never going to change because it's a line. So the derivative from the right is 1. But if you check it from the left, it looks like the derivative is negative 1. So the slope from the right is 1, the slope from the left is negative 1, and when you have that situation going on, here's what's happening. The derivative from the right, the limit from the right, is approaching 1. So as the slopes of the secant line approach the slope of the tangent line from the right, it looks like the derivative is approaching 1. And as you check from the left, it looks like it's approaching negative 1. So since these two things disagree, and my limit definition up here, okay, the derivative from the right and left would not agree, so the limit does not exist for the derivative here. So we would say it's non-differentiable at x equals 0. So this is the first example of differentiability. Another example, and I know that's really, really hard to kind of understand when you're thinking about it at first, but the next example is what we refer to as a cusp. A cusp is like if you have your bird. Here's another example of a derivative that won't exist. Now this one's a little bit easier to see, I think. So again, change colors. If I check the derivative from the right, it looks like the derivative from the right. Okay, all the slopes are positive, first of all. All these slopes are positive. But as I check them, it looks like they're going down. Okay, as I go to 0, where the cusp occurs. Okay, cusp is different from a sharp turn. It's curves coming into each other. So if I have these two curves coming into each other at 0, where they're kind of meeting, So the derivative from the right, they're all positive derivatives. These slopes are positive. But as the slopes, let me get my pointer here, as the slopes approach 0, it looks like these slopes are getting really steep positive. And what happens here is they're approaching positive infinity. The closer I get to 0, the steeper these slopes get, and these slopes are going uphill. So it's positive infinity from this side. If you check from the other side, the slopes are negative, and it looks like the slopes are getting really steep downhill. So from this side, you got slopes approaching negative infinity, and this side you got slopes approaching positive infinity. And again, since the limit doesn't agree from both sides, the derivative will not exist at this cusp. Okay? So there's another example. The next one is what we refer to as a vertical tangency. And a vertical tangency, your example of vertical tangency that I have is your line down disco curve. Okay, now let me grab my pointer again. If you look at the derivatives here again, looks like the derivatives here approach positive slopes here, and they're going to approach positive infinity, and here they're going to approach positive infinity. And here the issue at a vertical tangency is not that the slopes approach the same thing from both, it's not that they don't approach the same thing from both sides, it's that they approach a positive infinity slope. And so here's the deal, whenever you get a slope of infinity, and same thing really for the cusp, negative infinity, infinity, anytime you're approaching a specific value and the slope is approaching positive or negative infinity, really what's happening there, even in the cusp, is you're going to get a tangent line that ends up being vertical. And we really don't ever want to have a vertical tangent line because the slope's undefined. So really another way, so the way to look at the line down disco curve is even though the slopes are approaching the same thing from both sides, this is approaching positive infinity, and these slopes are positive, and they're just getting steeper as I go towards 0 from the right side. So the closer I get to 0 from the right and the closer I get to 0 from the left, they're both approaching positive infinity, which is going to give us a vertical tangency. And vertical tangencies, their derivative is always undefined. So now you have three examples, a corner, a cusp, and a vertical tangency where the slope's not going to be defined. Now, it's really important to understand, if you look back at all three of these functions, all of them were continuous. The corner was continuous, the cusp was continuous, and the vertical tangency was continuous. Because you got the absolute value, x to the 2/3, and the line down disco curve where the domain is all real numbers for all three of these. The last type of non-differentiability can occur at a discontinuity. Now if you remember discontinuity was referring to a hole, a jump, or a vertical asymptote, or an oscillating function. But specifically the hole, the jump, and the vertical asymptote. Anytime you have a discontinuity, you also run the risk of non-differentiability. If you have a hole, a jump, or a vertical asymptote, you're also going to have non-differentiability. So I'm going to look at an example of specifically where you're going to get this issue. So the example I have here is f of x equals x squared for x less than or equal to 0, and then 2x for x greater than 0. And so here's an example where we're going to take the limit definition, the limit as x approaches a. Now here's where this definition comes in. Here's how you prove non-differentiability. So when I look at this right here, you've just got x squared and 2x. We know x squared doesn't have a corner, a cusp, or a vertical tangency. Okay, and I'll tell you how to point that out in just a second, but we know it's just a parabola. And then 2x is just a line. So the problem is at 0 where these two pieces meet, or where they maybe don't meet. See, when I graph these, if I look at x squared, for x less than 0, it'd just be the left part of a parabola. And if I look at 2x for x greater than 0, it'd just be a line with a slope of 2 to the right. Now, when I look at this, what you actually form is a cusp. See, the derivative, if I look at the slopes from the left and the slopes from the right, I want to check to see if they agree. Now, graphically, it looks like they're not going to agree, because if I check the slopes from the left, it looks like the slopes from the left are approaching 0. See, I've got negative slopes, they're steep, and then they start leveling off to where it looks like the slope of the tangent line here is going to be 0. Okay? But then if you check it from the right, it looks like the slope's always going to be 2. So the slopes from the left, it looks like it's approaching 0, and the slopes from the right, it's going to approach 2. So how do I verify that? How do I actually show that without just looking at a graph? Well, you can do it analytically, which is using this alternate form of a derivative. So what you would do here, let me move this up here, is I would take my limit definition, I would check 0, and I'm going to check the limit from the left, and I'm going to check the limit from the right. So I'm going to plug it into my limit definition. If I check from the left, I'm going to use this piece. So here we go. I'm going to put x squared into this limit definition at 0. That's the problem. That's what I'm checking here. So f of x is going to be x squared minus f of a. You plug 0 in. You're going to get 0 squared is 0 over x minus 0. What I end up with is the limit as x approaches 0 of x squared over x. Try direct substitution, it doesn't work. So you get the limit as x approaches 0 from the left of x squared over x is x. Now I do direct substitution, it works, and I get 0. And that's what we were saying. We were saying the limit from the left looked like it approached 0. Now if you check the limit from the right, I'm going to use the bottom function. So I'm going to have 2x minus f of 0, because I'm plugging in 0, that's my f of a, and I get 0, over x minus 0 again. This time I'm going to get the limit as x approaches 0 from the right of 2x over x, which direct substitution doesn't work, so I simplify it, and I get 2, the limit of a constant's a constant, and again what we were saying from the right is that the limit approached 2. So the derivative from the left is 0, the derivative from the right is 2. You can see that here. The derivative from the left is 0, because remember, this is a derivative. The derivative from the right is 2, and since these two don't agree, it is non-differentiable at x equals 0. So you would say it's non-differentiable. Okay, I'm going to abbreviate, at x equals 0, and that's because of a cusp. And so we can see one example of non-differentiability. The last thing, and sorry this is taking so long, second here. I'm going to skip this using a calculator to derive. You already know how to do that. I showed you that the other day. You just plug it into y equals and then check your derivative at 2. And then I showed you how, and you can, and we'll talk about this more tomorrow, so I'll go back and catch that. But let me just finish up here this video. Differentiability, what we now know is that differentiability is going to break down in 4 places. Anytime you have, so our non-differentiability, functions are going to be non-differentiabilities at cusps, corners, vertical tangencies, and at discontinuity, any points of discontinuity. So what this implies is a very important theorem, is that differentiability will always imply continuity. So differentiability is going to become a real loaded statement, because when I say something's differentiable, it has to be continuous, because one of the places we get discontinuity, or one of the places we get non-differentiability, is when you have discontinuity. If you have discontinuity, it is always going to be non-differentiable. So, if the function is differentiable, then it has to be continuous. And some of you'd say, well, does it work the other way? If it's continuous, does it have to be differentiable? Because what I'm saying is that if it has a derivative, then it has to be continuous. Is it true to say that if it's continuous, it has a derivative? And that answer would be no. Because here's 3 examples of where it's continuous. Your x to the 2/3, your absolute value of x, and your x to the 1/3, and all of those are continuous, but it's non-differentiable. So differentiability implies continuity, but the converse is not true. Continuity does not imply differentiability. Okay? So only differentiability can imply continuity. Continuity doesn't imply differentiability because of these three examples. Now, if you're not proving differentiability, how are you going to be able to tell? Because in the homework, they're going to give you a bunch of graphs, and they're going to say, is it differentiable or not? All you got to do is look for corners, cusps, vertical tangencies, and discontinuity. If you see a cusp, it's going to be non-differentiable there. If you see a corner, it's going to be non-differentiable. If you see a vertical tangency, it's going to be non-differentiable. If you see any kind of discontinuity, a point, a jump, or a vertical asymptote, then it's going to be non-differentiable. These are all points of non-differentiability. Now, if you're given an equation, I can tell you how you can tell if it's going to be a corner, or a cusp, or a vertical tangency. Cusps, I'm going to add one more page here. A cusp will always be when you have x to the 2/3 power, it will have an odd denominator and an even numerator. If the numerator's even and the denominator's odd, it's almost always going to be a cusp. Okay? A vertical tangency, a vertical tangency is when you have a fractional exponent and the bottom is odd and the top is odd. So when the top and bottom are both odd, that's when you're going to get your vertical tangency. Okay? Now, some of you are probably asking, what happens when the denominator is even? Well, that's where you end up with usually a square root, and you only end up with part of the function, and usually a corner, a cusp, and a vertical tangency aren't an issue. So you don't even have to worry about that because if you have a even denominator, you chop off the left half of the graph because of imaginary numbers. So you don't even got to worry about an even denominator for cusps and vertical tangency. So the way you're going to tell the difference between a cusp and a vertical tangency is you'll have this odd denominator. If the numerator's even, it'll be a cusp. If the numerator's odd, it'll be a vertical tangency. And I'm going to show you why this works tomorrow. The final one is how you're going to tell if it's corner. Corners always happen when you have absolute values. If you have absolute values, you run the risk of a corner, okay? Or something else, like a jump or a hole or a vertical tangency or a vertical asymptote, which is also non-differentiable. So when you're looking at equations, if you see a fractional exponent with an odd denominator and an even exponent, you can say, oh, it's going to be non-differentiable at a cusp, and you just got to figure out where that happens. Sometimes you have to prove it with that alternate definition, but tonight it's mostly just going to be looking at graphs and equations and just saying why it's non-differentiable. So have a short homework assignment on non-differentiability, so finish that up plus the homework from last night, and I'll see you tomorrow.